Thank you very much. And as you said, this is joint work with Christoph and Gerhard. And it is about syntax splitting. And you might have heard about syntax splitting in belief revision. This was a problem that was mentioned by Parek in 1909. Basically saying if you have a prior belief set, which is given by A and B and logical deductions of that, and A and B come from different sublanguages, and then you learn about non-A, then you would expect that your revised belief set kappa star non-A would be Cn of non-A and B. Please note that this is compatible with AGM, but AGM would allow also the revised belief set to be Cn of non-A, non-B, so changing non-B. So basically, we transferred this to the notions of non-monotonic inference, which is closely related to belief revision. And here again, the idea is if you have belief and your new information comes in, which is split over the languages, and you would like to process this information, then you would expect this processing of information to respect syntax splitting. Here in our case, we assume that we are given a conditional belief base and that we do inductive reasoning from that. This is kind of a vague notion. I will make this precise on the next slide. And then if we have two formulas from a sublanguage and would like to know whether one of them non-monotonically entails the other, then we would expect that only the relevant part of the belief-based delta should be used, and these inferences should not be disturbed by information coming from the other sublanguages. So basically, we have here the two dimensions of syntax splitting given by relevance and independence, and the main contributions of this paper is to elaborate on these two dimensions and evaluate them in different frameworks. So first, what do I mean when I say inductive reasoning from conditional belief bases? Here we take kind of a very basic declarative approach. We assume that an inductive inference operator C assigns to each conditional knowledge base non-monotonic inference relation, and the connection between the inference and the given set delta is quite basic. We expect that if there is a conditional in delta, B given A, then we would expect that the induced inference would then sanction from A, we can non-monotonically entail B. And moreover, in the limit case when we don't have any conditionals, then actually non-monotonic inference boils down to classical inference. I think these are very basic requirements. And as I said, there is not a really defined notion of inductive reasoning, though many people are using it. For instance, system P, you might have heard of this as an axiom system of different axioms, and if you then close your inferences under system P, then this would give us an inductive inference operator. There are several well-known semantics for inductive reasoning. First, by, for instance, total preorders, and then you can define a non-monotonic inference relation by saying A non-monotonically infers B on the base of this total preorder if AB is more plausible than A and non-B, and of course from this you would obtain a model-based inductive inference operator. And for instance, preferential entailment, which is closely related to system P, would be an example for that. And you might use Pohn's ranking functions, which are similar to total preorders, but assign a natural number to each possible world. And here, non-monotonic inductive inference is even simpler. You can say that from A, we entail B if the rank of AB is less than the rank of A non-B. So again, if AB is more plausible than A and not B. And again, by assigning to delta such a ranking function kappa delta, we obtain again inductive inference. Okay, here an example would be system Z by Pearl. And the general link between conditionals and inferences, which has been already expressed in the TI postulate, is a conditional in each of these semantic frameworks is accepted if the non-monotonic inference holds. Okay, what is syntax splitting? Our basic setting of syntax splitting is we are given a set of conditionals delta, which is the union of two subbases delta 1 and delta 2. And these subbases are specified over sublanguages sigma 1 and sigma 2, which are disjoint. And the union is the whole set of signature elements. Of course, it suffices to look at this simple case where we just have a splitting into two subbases. Of course, we can extend this to having several subbases. And then we would like to talk about inference over the sublanguages, and a very powerful concept to restrict some technical concept over the whole language to a sublanguage is marginalization. And this can be defined very easily for inference relations, given that we have two formulas A, B from the sublanguage, then the marginalized inference relation over the sublanguage is just inherited by the general inference relation. And for total preorders, this is again inherited directly, immediately from the total preorder over the whole language. And for ranking functions, the concept of marginalization has already been introduced by Spohn. It's again the marginalized ranking function. So let's now look at our axiomatizations of relevance and independence, starting with the general inference operators, the inductive inference operators. And relevance says, as I said, the aim is to model that only the relevant part of the belief base should be used. Again, if A and B are from the same sublanguage, then we have that from A we can entail B if and only if this inference holds over the respective sublanguage, which means that the marginalized inference operator on this sublanguage is the same as the inference operator over delta I. And independence, then these inferences should be independent from other sublanguages. This is specified in this way, that if I know A from A, I can entail B, then even if I extend A by C coming from the other sublanguage, this should not influence the entailment relation to B. And then syntax splitting is just the combination of relevance and independence. And let me show you in this example that syntax splitting is not just some kind of an artifact, which is nice to have, but really syntax splitting can help us reducing global to local inferences, so to reduce the complexity. Given this very simple example, I apologize for using penguins and birds again. We have here flying birds, and penguins are birds, and penguins do not fly in our delta 1 subbase, and then that dark objects are not visible during the night. Of course, we have such a syntax splitting here. And then if we would like to know whether some inductive inference operator sanctions the entailment that dark penguin birds don't fly, then first by independence, we can omit the D coming from the other sublanguage. And then by relevance, we can again forget about delta 2 and just focus on the inferences sanctioned by delta 1. So this can help us crucially to reduce complexity of inference, which is quite practical. So system P satisfies relevance, but not independence. And I will go quickly over this. Of course, for our inductive inference operators, assigning to each conditional knowledge base a TPO, a total preorder, then relevance and independence can be formalized in this way. And here we have a representation theorem. If we have an inductive inference operator, which is implemented via a total preorder, and then the inductive inference operator satisfies syntax splitting exactly if and only if the TPO satisfies the TPO version of syntax splitting. So we can just check, looking at the total preorder, whether the induced inference operator would satisfy syntax splitting. For OCFs, again, same game. It's really can be very nicely, in this framework, we can very nicely express syntax splitting in this way, again, which is the same what we did before, of course, using then the OCFs. And here we have a very concise representation for syntax splitting for inductive inference operators induced by OCFs. It's just by this equation here, the kappa delta should be the sum of kappa delta 1 plus kappa delta 2. So we have really here very concise characterization. This is due to the arithmetic structure of OCFs. Here, system C satisfies again, not syntax splitting, it's just relevance but not independence. So we have to look at the C representations. You might have seen it before. C representations are kind of a penalty system. And here, what we do here is that we associate to each conditional knowledge base via a strategy, a solution vector of these penalty impacts. And now we can talk about whether such a C representation satisfy syntax splitting. We can investigate the strategy, and if it satisfies this axiom here, IP, the impact preserving strategy, which means that for any subbase, this penalty vector is chosen in the same way as for the whole conditional knowledge base. Then, if this is satisfied, then our strategic C revision satisfies syntax splitting. And if we can do even without strategies, if we consider the skeptical inference operator given by all C representations of a conditional knowledge base, then again, this also satisfies syntax splitting. So we have C representations as a proof of concept of syntax splitting in non-monotonic belief revision, non-monotonic inductive inference, sorry for that. So what we did further more in the paper, we defined a qualitative notion of conditionalization for total preorders and characterized and defined independence of subsignatures in terms of this qualitative conditionalization. Thank you very much.